The moment of inertia is the summation of all of the little bits of mass dm at the location of dm. So what in the world does that mean? That means if you have a particle, okay, a particle. So here is a light rope, so light that it's just a dotted rope with a mass on the end of it that's concentrated with a really small radius. So think like a BB, a massive BB. If you don't know what a BB is, then look it up. All right, you'll shoot your eye out. Okay, so if this mass right here, M, is moving in this circle that I'm trying to draw, that's not supposed to be an oval, but kind of a flat circle, that mass right there is all located at the same position. So the R doesn't change, it's the same, and the mass is the same at every place R as it goes around the circle. So really, if you were to find the moment of inertia, it would just be r squared dm, like from 0 to m, and that would just be mr squared. All of the mass is at one place. Pretty easy. Now, if we take that particle, so imagine that particle is like a lump of clay, and we take that lump of clay with a mass m, and we make it into a long, skinny snake. Remember when you played with Play-Doh? And you can take that mass and make it into a long, skinny snake. And you make it into such a long, skinny snake, then you can actually make it have a circular shape to it. Okay? So you have the same mass as the particle up here, but it's just smeared out over to make a circle, basically. So the whole mass is still M. Now, because we have smeared the mass into this circular shape, we have created a linear mass density. That is mass per length. So think about it being super thin, so thin that it doesn't really have volume to it, but it's just one-dimensional, or it can be modeled as one-dimensional. So if I want to find the moment of inertia of this shape of mass m, I need to integrate r squared dm. Now dm is a little bitty bit of mass anywhere, so there's a little dm, and it's at a distance r from the center. Here's an identical little piece of dm. Because the linear mass density is the same, could you take a chunk of the hoop at any point, and as long as it's got the same arc length, you would have the same mass? Because the density, the linear mass density, is the same. Okay, so I need to define dm in terms of the circle. So if lambda is my symbol for linear mass density, that would be mass per length, which I could also write as a little bit of mass and a little bit of arc length. So if this is a chunk of dm here, then this tiny little arc right here is my dl. Okay, so, but the length is dependent on, that little dl is really the arc length. And if you recall, arc length, S, is equal to r times theta, right? So if I want to look at a little bit of that arc length, it's because I've had a little tiny change in angle. So instead of S, we're using L. So L is equal to S. So this would be dl. R stays the same. The radius of the hoop stays the same, but it's a little d theta. It's a little bitty tiny. If you go back and look at my little blown up version, it's a little tiny change in the angle. So this would be our d theta there. D theta. That little tiny change in angle as you go from the beginning of dm to the end of dm. So we're looking at a little bitty piece. Okay. So that means that lambda could be equal to dm, the ratio of the mass to the arc length. So I just made a substitution. Which means then that I could come up with an expression for dm in terms of the mass per length, which should be just the total mass of the hoop divided by the circumference of the hoop, right, times r d theta. So now that I've got this function defined here, I can go back in and substitute it right there. And now I can integrate all the mass as I go all the way around the circle. I can sum up all the little bits of mass. So I would be equal to the integral of r squared. dm is lambda r d theta. And we're going to go all the way around the circle. So what are my limits? 0 to 2 pi. Very good. Okay, so then I can combine the r's. Lambda is a constant. So we'd have what? R cubed lambda from 0 to 2 pi d theta. Is that correct? So then we'll have r cubed lambda times 2 pi is the moment of inertia. Now, if lambda is a constant, meaning the linear mass density doesn't change, the hoop isn't heavier on one side just because it has a clump of mass over there, then that would be the mass of the hoop divided by the total length of the hoop, which is also known as the circumference, okay? So 2 pi r. So let's make this substitution back in over here so that if I have the mass of the hoop, I can find the moment of inertia. So I have r cubed times the mass of the hoop over the circumference of the hoop times 2 pi. Now what's that give us? You have an r cancel with an r here. We have a 2 pi and a 2 pi, and we get mr squared for the hoop. So now if we look at a disk, so take the same mass, the moment of inertia of a disk, solid disk. So here's my mass m. And now instead of it being all concentrated on the edge of the hoop, it's smeared throughout. So we've made a pancake of mass. Thin pancake of mass. And we're going to rotate it about the center axis, like the z-axis. Imagine it coming out at you, the z-axis. And just to make sure we're clear, that's the same z-axis I was using here. We're rotating this guy around the z-axis. And this we're rotating about, I guess that's the y-axis it was rotating around. Okay. So maybe you have, maybe you haven't, but it's not going to be the end of the world. Have you ever found the area or the volume of an object by modeling it as lots and lots of layers built on top of each other to make up the shape? Shell method? Okay, so it's not the end of the world. If you haven't done this, I'm just going to kind of give you a quick and dirty physics explanation of it. But if you imagine having a length of string and you bend it into a circle, And then you have a slightly bigger length of string, and it's just big enough to go around the edge here. And then you have another length that's just big enough to go around here, and just big enough, and we keep layering and layering like this, just more layers and more layers. We can eventually get a disc by building up these layers. And each one of these layers has a length. So think of it as like a flat piece that has a length that in terms of the circle would be 2 pi r, but has a little teeny tiny thickness of dr, because as I get further and further from the circle, from the center, there's a little bit of mass here, dm, and it has a little bit of thickness to it, dr. That's going to depend on where I am from the center of the circle. So if the moment of inertia is the sum of all the little bits of mass at their radius squared, and this disk has high symmetry, and this disk has a constant surface area density, so sigma is mass per area. That's a lowercase sigma. So sigma could be modeled as a little bit of mass distributed over a little bit of area. So zooming in on this spot right here, if I were to zoom in on it, I would see, so here's my zoom in picture right here. I've got this now hunk of mass here. That is our dm, and it has a little thickness dr. And I'm going to build this up as lots and lots of basically little hoops with a slightly bigger radius, a slightly bigger radius, a slightly bigger radius, until I finally get the full shape. Okay, now dA. Area of this whole thing is the 2 pi r, the length of each one of these strips that I'm going to bend into a circle and layer on top, times their thickness. Isn't, nope, that's not an A, that should be an R, times their thickness, dr. So 2 pi r is the length of the layer that I have bent into a circle. Dr is the thickness, or the height. And length times height, or height times length, gives you area. So that means that sigma could be dm over 2 pi r dr. Therefore, dm can be written as sigma, the mass per area, times 2 pi r dr. So then if I substitute that into our moment of inertia equation, r squared, now dm is sigma 2 pi r dr. So I'm going to integrate, I'm going to add up all the layers of mass from 0 to the final radius of our disk. Sigma is constant, 2 pi is constant, so I'm left taking the integral from 0 to capital R of r cubed dr. So what would that give me? That would give me sigma 2 pi r to the 4 over 4 minus 0 over 4, which is 0. All right, so now what sigma, just like Kahan asked, so sigma is the mass per area, and the area of my disk would be pi capital R squared, if capital R is the radius of my disk. So if we do a substitution, I is equal to m over pi capital R squared 2 pi capital R to the 4 over 4. And what does that reduce to? Is it 1/2 mr squared? So that's I for a disk. So the moment of inertia of a disk is, with the same mass and radius, is half the moment of inertia of a hoop with the same mass and the same radius. So if we now look at this case where we've got here's the ceiling, here's an example, here's the ceiling, and here's a support rod, and here's a pulley, and that pulley is a solid disc now that can rotate, and there's friction, so this cord over here has to have a different force, Ft1, than this cord over here, Ft2, and in order for it to rotate, if we have a little mass m and a big mass m, just like a teeter-totter, if you imagine the disc is like just a funky teeter-totter, where here's the diameter, here's the pivot point where the disc can rotate, and you've got a force from the tension on one of them, you've got a force from the tension on the other one, and if this thing is going to rotate, I better draw these to scale somewhat anyway. If it's going to rotate, these two forces are out of balance. They're at the same distance r because they're a rope draped over this disc, but now the disc has mass. So some of the gravitational energy that the big mass has here, so if you let this system go, would the little mass go up or down? The little mass would go up, the big mass goes down. The big mass has gravitational energy. It's going to be converted to kinetic energy of that mass that's the big mass that goes down. It's going to be moving, so it's going to gain some kinetic energy. It's also going to transfer some of its potential energy to the gain in potential gravitational energy of the little mass, and the little mass is going to be moving, so it's going to have kinetic energy, and this disc is going to rotate, so it's going to have rotational energy. If you wanted to reduce the effects of the pulley, what could you make this disc out of? Or how could you redo this design? Make it a hoop. You would reduce the moment of inertia. Or take out the middle by reducing the mass, yes. Okay? But if you had to have a particular mass, having a disc would have a lower moment of inertia. Right? So, if you've ever noticed, a lot of times there will be, like our pulleys that we used that go with the carts, they all have sections cut out in them. It's not just to make them look cool, it's to reduce their mass. So they have even smaller mass so that it doesn't take as much to get them going, and therefore doesn't take away as much of the energy of the system. It doesn't cause as many effects. If that disc is small in mass, then it doesn't matter overall. But now our discs are going to be heavy and have mass and need to be balanced. So just like we've done before, we would draw the force diagram. So the little mass goes up, and that's the positive direction. The big mass goes down, and that's the positive direction. The little mass is going to have a tension force up. I'm going to call it Ft1. It'll have a smaller Fg little m because unbalanced forces cause acceleration. The big mass will have a tension force up, Ft2. It has to be greater than Ft1, otherwise it's not going to make the disc rotate. And then this gravitational force has to be even bigger. And then on our disc, we have to have an equal but opposite direction FT2 and then our FT1. So this guy goes up, and I can see from my unbalanced forces. This one goes down, as I can see by my unbalanced forces. And which way would my pulley rotate? Clockwise, counterclockwise? So make the direction of the motion positive. So now, just like before, I would sum the forces in the y direction on my little mass, and the FT1 minus FG of my little mass would equal MA. And I would sum the forces on my big hanging mass in the y direction. And now my FG of my big hanging mass minus FT2, because down is positive in this orientation, would cause capital M, big M, to accelerate. But then over here, I have to sum the torque. So let's go back real quick and just look from Friday right here. So our torque is how the force is oriented to the axle that causes the thing to accelerate. Fr is the torque, and that torque causes an angular acceleration. It causes that system to rotate. So let's go back over here. So this whole disc is going to rotate. It has a moment of inertia. Just like the masses that you put on the rod and let spin, those have a moment of inertia. So now FT2 is going to cause a positive torque because it's in the, that force would cause it to rotate clockwise. But what does FT1 do? It really applies a negative torque. So FT1, also located at a distance r, the radius of the pulley, would equal I alpha. Now, just like S is equal to R theta for the arc length, and V is equal to R omega for the angular speed, then linear acceleration is equal to R times alpha. And we can make a relationship between these linear accelerations and this angular acceleration. So I want to continue to apply this and get you comfortable with summing forces and summing torques before we try to do a lab. Okay? All right, that's it.